but you will realize you don't have to know anything technically. Trust me. Yeah. So particularly, the keyword is non-equilibrium thermodynamics perspectives. So let me introduce RG flow in conformal field theory in 2 dimensions and C theorem. As you can see, the C theorem can be regarded as a no-go theorem in dynamics. You may hear about no-go theorem. For example, Nielsen and Ninomiya theorem usually appears in topology. But C theorem is also such kind of no-go theorem, but not in statistics, but dynamics, which means that suppose try critical ideal quantum critical point. If you recall some liquid gas solid phase transition, and we know the tri-critical point. Now you introduce some deformation, relevant deformation, whatever, you just add some pressure, magnetic field, whatever. Then this critical point becomes destabilized, which can go into ideal quantum critical point. But reversely, if you introduce some relevant deformation at this ideal quantum critical point, you cannot access this fixed point. That's the precise meaning of no-go theorem at IR, if you go to low energy domain. Frankly speaking, to me, C theorem may be the most general no-go theorem in physics, but this is my just personal opinion, not justified. Then you may ask, if you have very some restricted stable condition, there must be reasoning. We learned that usually gapped system is stable. But if you have a massless excitations, it gives rise to huge entropy. There must be some stability mechanism protected by symmetry. We know that Goldstone theorem, and also some topological protection, blah, blah, some gapless edge state. So in this case, I would like to discuss some such kind of mechanism, either symmetry protected or topology protection. This is my motivation in the thermodynamic perspectives. So let me review the RG flows. Frankly speaking, so I think previously I understand this one, but when I prepare this talk, my understanding is not sufficient. So I just used a very textbook level review. So now you consider some conformal field theory, IG or whatever you can imagine. Now you consider some relevant deformation, some mass parameter, mass term. So its scaling dimension is given by delta alpha and coupling constant. Now this system becomes unstable, go to some new fixed point. Then you can easily calculate one loop beta function. So this is this one. Then you can consider some second equivalent expansion. Then G alpha, G beta, O alpha, O beta in the exponent. Then cumulative expansion. Then O alpha, O beta, you have C alpha, beta, gamma, O gamma, O. C is so-called operator product expansion coefficient. This is constrained by some conformal symmetry. Then you can easily find that. So now G alpha, G beta, and blah, blah, blah. You can have this term. So this is the beta function. So from original system UV fixed point, there is some RG flow by this term. Then, but interestingly, you can see this is power. You can reformulate this in terms of the so-called C function. So as you can see, this beta function can be derived from this gradient-like expression. Then the beta function is given by the gradient of this mother function. Here, gradient is given by in the coupling parameter space. So, if you consider this one, then you obtain the beta function. Of course, this is not the derivation. From this one, you read off. What Chamonix-Coff showed is that this so-called C function is monotonic. So that's the main statement of the C function. I want to figure out, is there any some symmetry perspective or something like that for this function? That's my question. So this is very textbook style review. Then if you open any conformability textbook, then there is some conservation law of energy momentum tensor. Energy momentum tensor is a generator of conformal transformation. Conformal transformation is some extended version of scaling symmetry that we learned in statistical physics. So this is conservation law of energy momentum tensor and in complex coordinate, and this is trace of energy momentum tensor. Then Chamonix-Coff introduced these correlation functions, this one. Then just plug in here, then he obtained this equation. Based on that equation, you can derive, you can show this weird some combination is monotonically decreasing. H is the trace square correlation function is always positive definite. You can reformulate this in terms of some evolution equation. This is so-called Kalan-Jumanjic equation, RG invariant equation. So any partition function or correlation function, free energy, whatever it is, it should follow this one. So this is the scale, and this is the beta function, this is the coupling parameter. This is just given by some applying the chain rule. If you apply the derivative R or some energy scale, it is given by some partial and coupling, just applying chain rule. And so from this C function, you can calculate this right-hand side. So this left-hand side, and you can calculate. Previously, I showed some trace of energy momentum tensor. Trace is given by this one and this square, beta, O alpha, O beta, beta alpha. So from this one, you can have this one. And yeah, this is the correlation function of given this one. This is beta function. As you can see, this is basically beta scale. This is so-called Chamonix-Coff metric in coupling space. But anyway, the main point is that this is negative, which means that from this one, this C function is monotonically decreasing. That's the main point. So whatever the proof is, the main point is the so-called C function is monotonically decreasing. So anyway, let me skip this part. So then we learn. So some error of time, we always learn what is such a quantity? Entropy. So my question is, this C function like quantity has to be related with some entropy quantity. So how can I actually? This question is not asked by Mike. I mean, already asked, particularly so-called Perelman. Perelman is the Perelman who proved Poincare conjecture. He also introduced his entropy functional. So, inspired by so-called C function, he extended his analysis to some geometry. So, I also use this one. It's very clear. Non-equilibrium thermodynamic perspectives for the monotonicity of the renormalization group flow. That's the title of this talk. So actually, they only know the only thing that I know about non-equilibrium thermodynamics is about Langevin equation. So let me try to discuss some reformulation of Langevin equation. So Langevin equation has very long history. There are many types of reformulation. So here, this is the position of the Brownian particle, time t, and this is the force. Force is given by conservative force and external force. And psi is random noise. So lambda t is external protocol for non-equilibrium. Then this noise satisfies some this noise is given by some randomness. So this diffusion coefficient is given by mobility and temperature, satisfying fluctuation dissipation theorem. So this is everything. This is the main technique. But the only technique that I can use is this one. So everybody knows this is delta function and f prime. Now in f, I inserted the Langevin equation. Then to make one, I need some Jacobian factor. That's it. This is the only thing. Then with this formulation, this kind of formulation has naming. So-called 5D Popov procedure. So quantification of non-abelian cases, blah blah. So you can use this one. But essence is like this one. Then with this one, instead of equation, I consider some generating function. Now I consider any quantity should be given by averaging of random disorder. And so now have this is 1. Then introduce some Lagrangian multiplier field, P, canonical momentum, and determine the so-called introducing some Fermion field, so-called ghost field, you can reformulate in terms of this path integral formulation. It's very easy algebraic manipulation. Then if you integrate out this noise, then you obtain this one. This is purely topological, which means that whatever you calculate this one, this value is 1. Because this is 1. This is 1. Yeah. So this is so-called, also has naming. So instead of solving equation motion, just reformulating in terms of path integral way, then you can deal with it. Then the question is, from this expression, I will introduce entropy and symmetry. That's the main motivation. So I think that this is very clear. Very easy and straightforward. Although I will discuss it, but not here. So the previous action, reformulating Langevin equation into some path integral formulation, has the so-called PRST symmetrics, but I will discuss it. And I will claim this is the protection mechanism for the monotonicity of the algebraic flow. Yeah. But anyway, to discuss entropy production from the Langevin equation, I will consider some probability distribution. So this probability distribution is defined by, so probability means that at time t, at position x, the probability p means that the probability to find a particle at position x and t. Then, yeah, this one, you can show this satisfies the so-called Fokker-Planck equation. So this is very textbook level, we already learned. Yeah. Then the path integral formal solution of this Fokker-Planck equation is given by this one. This is the same as what I showed before, as it has to be. So based on this formulation, Seok introduced his entropy functional. So this one, he considered Gibbs entropy. So previously, told you Boltzmann entropy. Now we consider some Gibbs entropy. From this one, path dependent, trajectory dependent gives entropy. Then from this one, you have some so-called system entropy. Then this corresponds to the thermodynamic entropy. In equilibrium, this expression is reduced to the usual thermodynamic entropy formula. Then Jalbert calculated the time derivative of this entropy, system entropy, but he found some additional term. To cancel such additional term, he introduced some environmental entropy, naturally given by some heat dissipation is given by force, Fx dot some power. So from this one, everything are cancelled. So total entropy is given by this one. As a result, you can show that this part vanishes, this term, using the equation of motion, x dot is j, so you have always positive definite. So this S total is not the thermodynamic entropy, it's the total entropy. So this is so-called entropy production, monotonicity of arrow of time. So yeah, always entropy is increasing. Yeah, this is the, so I will connect the C theorem, C function with this entropy production argument. That's the, based on the path integral formulation. This is the statement. If you recall, previously, derivative of the C function is given by some beta, some metric and beta square. So this corresponds to J here, J, you will see. So then the question is, how should I reformulate the RG flow in terms of the path integral, and like this one? But as you can see, either Fokker-Planck, so the flow chart is Langevin equation, Fokker-Planck equation, and path integral formal solution. This is Schrödinger equation and Hamiltonian and Feynman path integral, this kind of thing. So given equation, you can easily reconstruct the path integral. Wait, actually this is done this is not by me, already from 1960s, 70s, so see, now let me consider the partial function. If, so usual standard Wilson analogy, separating slow and fast degree of freedom, you integrate kind of fast degree of freedom, then you have some effective potential resulting from heavy degree of freedom, then this coupling constant, so yeah, this is given by some effective potential integrating by heavy degree of freedom at some length scale, then coupling becomes low, the cutoff becomes lower, then at lower cutoff, this becomes renormalized given by some beta function. Here the main point is that I assume beta function is given by some gradient flow, gradient expression in the coupling parameter space of this effective potential. Yeah, this one. Usually, if you recall Wilson analogy, if you integrate a heavy degree of freedom, usually you cannot avoid some non-local terms. So, but if you consider only coupling parameter, if you recall some beta function, previously G and G cube, and Kondo effect, JK square, and some others, then all is some local power, then you can, if you integrate this one, if you consider some expansion over the coupling, then you can realize, yeah, in many cases, but not completely general. This is the main assumption. Yeah. Sorry, okay. Again, I consider, again, this one. Again, I repeat and repeat. I mean, if I have time, I will discuss some metric variable, yeah, that looks fancy, but the same thing. So this is coupling function, beta function, and also Jacobian factor, and then this is Lagrangian. But the main difference compared to Langevin equation, I have to introduce this effective potential, which results from integrating out high energy fluctuations. That's the main point. So the only difference is this one. Without this one, this looks essentially the same as the Langevin equation reformulation. So in this respect, this reformulation is not purely topological. Then Lagrange multiplier field and blah blah. Then Fourier-Popov method. And this is completely standard textbook material. I consider some deformation of coupling parameter. Instead of usual action, I added this. So for the coupling function, around the average value, I consider some Gaussian fluctuation. Then I obtain this kind of term. So this term corresponds to, suppose if you have some precise force power interaction originally, if you derivative lambda and square, then you have ace power. So usually irrelevant deformation. Then from this one, you can promote this effective coupling function into the complete dynamic variable. So if you forget this action, this becomes completely the same as the Langevin equation formulation. Purely topological. If you integrate out, this is just one by construction. But now you have effective potential, which results from integrating out quantum fluctuation, heavy degree of freedom. Interestingly, original field theory is given by d dimension. Now you have t plus 1 dimension. Usually, in holography, well reviewed in previous talk, the extra dimension is interpreted as some invergent energy scale to describe some algebraic flow of the original boundary conformal field theory. So now, basically this is my interpretation, but anyway, now, the only difference compared to Langevin equation formulation in interaction with this effective potential term. This will change pretty much compared to the naive Langevin equation, but the monotonicity proof for some other case, so basically not much important. But this is the main point. So vertex fractions given by this algebraic flow, and also some effective self-edge corrections are self-consistently introduced in this description. That's the main point. But then the question is, from this expression, I will introduce some entropy and I will investigate some symmetry. That's what I'm doing. From now on, this is almost a textbook level example. So, in Langevin equation, from the previous effective action, already people found that some so-called BRST symmetries. If you recall, Schrödinger-Kelly's formulation, you have you double the field degree of freedom, so forward in time and backward in time. If you set the two fields identical, then the partition function becomes 1. That is called unitarity condition, unitarity symmetry. And this unitarity was topological constraint, which is partition function 1, is described by some transformation generator Q and Q bar. I will discuss what it is, but technical detail is not much important. Such unitarity symmetry is described by fermionic generator. This is completely well known in Langjaman. Even in Langjaman equation, you can easily find it. And there is also another symmetry, so-called KMS symmetry, Hubo-Martin-Schwinger symmetry. Essentially, time reversal transformation. So from T to TF minus T, TF is the boundary time, final time. Then the Schwinger-Kelvin partition function remains invariant. That kind of symmetry can be reformulated in terms of some additional diurnal fermionic charges. So based on Q and Q bar and D and D bar, you can define so-called BRST symmetry. You may hear about BRST symmetry from non-abelian phase theory quantization. Also completely the same. Yeah. But in that case, you have only one, but we have two. This is natural. When you try to pass into a reformulation for any some equational motion, basically you have this kind of symmetry. Then I open some textbook and paper. I'm trying to extend some space with some auxiliary Grassmann variable space called superspace formulation. But just open textbook, so I also trying to construct this superspace formula, this source term and field term, originally coupling function, canonical momentum, and this Grassmann variable. Just based on this one, you can consider some transformation. If you apply BRS charge into this field, then you can find it. For my case, I made a little mistake, a sign and some derivatives. But anyway, it is very straightforward. Just in this one, then you find this one, which means that original lambda changes into C, and C bar transformed into pi. This is what it means. And also Q and Q bar. It's completely straightforward, and everybody can do that. Yeah, but for me, it was not easy. I made a lot of mistake to sign and blah blah. And even if I'm in Langjaman system, it's completely well shown, and I match symbol by symbol, even if so. But based on this one, you can reconstruct some. This effective action function in terms of this manifesting supersymmetry way. Yeah, this is the neglecting this one. This part was already constructed for the Langjaman case. The only difference is that I introduce some effective potential which results from intuitive heavy degree of freedom. That's it. That's it. So it's completely, so now based on this one, you can easily construct some word identities where the correlation functions has to satisfy. Compared to if we, in the Langjaman case, if we consider beta function some force, if you consider no force that has to satisfy so-called fluctuation dissipation theorem. This is X, T, P. So retarded Green function, advanced Green function, retarded Green function minus advanced Green function is Kelvin Green function. This is fluctuation dissipation theorem. From the previous symmetry, BRST symmetry n equal to supersymmetry, or KMS symmetry condition gives rise to this generalized fluctuation dissipation theorem. So here, due to the presence of beta function, some force, it is modified. Then you may ask, so what? Unfortunately, I cannot answer that question. This is a very important point, but yeah, at present I have no idea how to use this correlation function word identity. Yeah, for. So finally, almost finally, let me discuss some. As the case of Langjaman equation, instead of position, I consider some coupling. Now I have this one. As I told you, the only difference is some effective potential. And this probability distribution has to satisfies the modified Fokker-Planck equation. You can easily derive it. So previously in Langevin equation, Fokker-Planck equation, there is no this term, but the presence of this term does not affect the monotonicity problem. So this is previously we have first term, so diffusion constant previously. Then so this is conserved current, so that gives us some. So frankly speaking, I mean, usually if you recall Noether theorem, when you consider some conserved current, you have to find some symmetry. And frankly speaking, I'm not sure what this gives some compared to the previous class integral formulation. But anyway, again, I consider some entropy following Jaipert, system entropy, then I think there's some, and just derivative, this one. And if you plug in the Fokker-Planck equation result, you have this term. So additional term, this part, and this part. So this is fx dot, and there is additional term. So this I assume some environmental entropy. Then I add this one. Then only this one, the same as the Jaipert result. Then finally, this total derivative vanishes. So this is given by basically beta square. So this is exactly given by the C theorem. So if we recall the C function, this part is given by the derivative of the C function. So this is the one of the main results. So whatever it means, we show the monotonicity of the energy flow. So just by reformulating, but here may not be completely clear the direct relationship with the C function that I showed before. But what I want to say here, if I neglect the effective potential generated by integrating our high energy freedom, it is essentially given by the same as the C theorem. But I added some effective potential. So although not rigorously proven, but it seems that this is some non-perturbative extension of the original Java logic of C theorem. This is the main result. How much time do I have? Finish. Almost. Exact time. Okay, that's it. Thank you very much.
Question, please.